Here we have the mathematical model, all the model integrated, whole model here. And here also we have the graph of the model. Okay, now we start the modeling of it for solver and solving it and do some discussions on that. As the previous examples that we did together, we start with decision variables, and I'm gonna write all of them here. And we start with x1, 2, x1, 3, x1, 4. Okay, here we have 14 decision variables. And just to Okay, now we are done with definition of our decision variables, and like the previous one, just we make it stood out by this color and borders, and after that we go for the objective function. Okay, I'm gonna write the objective function here, and objective function is x12 plus x13 plus x14. So it would be x12 plus x13 plus x14. Okay, now we have also our objective function. Now it's the time to go for the constraint. How many constraints do we have here? Okay, we have 7 nodes, so there are totally 6 constraints for the nodes, because if you remember, we talked about the fact that for nodes 1 and 7, totally we have 1 constraint. We have 7 nodes, so totally there are 6 constraints in terms of nodes. And okay, so 6 constraints for the nodes, and also we have some more constraints regarding each arc. So it is in fact the first model that we are doing that we have constraint for the nodes and for the arcs. And since each arc is associated with one decision variables, and totally we have 14 decision variables, so totally we should have 20 constraint, if I'm right. So it is 20. Hopefully it is right in the calculation. And let's make it bold. You should have no problem regarding definition of the constraint. They are similar to the previous one. So for example, for C1, I start equal, and here we have C1 x23 plus x25 minus x12 minus x32 And since we don't have any value on the other side, so we are done with this constraint. Like this, we continue for the remaining constraints that we have until we cover all the constraints related to the nodes. Now we have all the constraints regarding the nodes are written, and the last one here, it is regarding the node 7 and node 1, that is x12 plus x13 plus x14 equals to x57 plus x67, that we have it here, 67. Okay, now we continue with the constraints regarding to the arcs. We start with arc x12. So when we want to write the constraint, we go for equal. We have x12 minus here x12 minus 5. The constraints related to the arcs are very short and quick to handle. The next one, let's go for x13. So equal x13, that is here, minus 6. The related constraint, it is this, x13 equal or smaller than 6. So we have C19. C19 is x13 minus 6. And like this, we continue until we cover all the arcs. Now the model is fully formalized in Excel, so we can call upon solver to solve the model. Okay, here we have the solver. Let's go for the objective function. Okay, P21, correct. And it is maximization. After that, we go for the decision variables, 14 decision variables. Then we go for the constraints. Okay, for the constraints, you need to pay attention. The first 6 constraints, all of them are type of equal to 0, but after that, all of them are equal or smaller than 0. So I get the first 6 ones like this and equal or smaller than 0, and I add them. And after that, I go for constraint 7 to 20, that all are related to the arcs, as you can see here, and all of them are the types of equal or smaller. So I'm gonna put this 0, and now we are good. And also the last one is unconstrained variable, non-negative. It is in fact related to the non-negativity constraint. So now we should be fine to punch the solve button, because we don't have any binary variables or anything like that. So let's solve the model, and we got it. So here, let's make some changes and make it decimal to 1 decimal. Okay, it seems we got the answer, and the objective function shows it is 15. So 15,000 cars is the maximum flow possible between 1 and 7 with the current network. Now I'm going to show you in a better way that what does it mean regarding this graph that you see in front of you. Okay, let's check it. X12 is 4. So here it says we have 4. From this x1 3, we get full capacity, so I'm gonna write it like this. x1 4 is full capacity. x2 3, it says it is 1. x2 5, it is 3, so full capacity. x3 2 is 0, so it is not gonna use this road. 3 4 is 0, so it is not gonna use this as well. So let me, isn't it amazing that we can get this type of exact answers when we do a model and we get them this much well organized with solver? Okay, 3 5 is okay. Here you see 3 5 is 5, but the maximal capacity here is 3. It's because of the typo here, and it is 5, as you can see. So let's change this one to 5, and because I don't want to change any other things, you can solve it any other way. But as you can see here in the modeling, there is a typo, so we have to change it. So 3 5 is 5, 3 6 is 2, and 4 6 5 full capacity, 5 6 0, so they are not going to use this road. 5 7 is 8, 6 5 is 0, so this route is never gonna be used, and x 6 7 is 7. So the only problem that we got was that, because here we have 3, but here in the model it was 5. So I decided to continue with the model that we had because I didn't want to repeat the solving process. But you can continue your model with this one. If that's the only difference, no problem with that. Now, the traffic management of the city can claim that they can handle the traffic load of 15,000 per hour. Why? Because they said that we are going to handle 4,012, 6,013, and 5,014. So totally they can get 15,000 input from the entering point of 1, and also they can handle the 15,000 from the exit point of 7. From the other points, okay, what will happen to this 4? This 4 will give 1,000 to 2 3, and will give 3,000 to 2 5, so no problem. And after that, this 1,000 that they send to 3, and 6,000 from 1 to 3, it is totally 7,000 that is going to be handled through 3 5 and 3 6 5 2, as you can see here. And also the 5,000 that we give to 1 4 will be handled easily through 4 6, and you see is working amazingly. All the constraints are covered and everything is being engineered professionally because of the well-structured model we designed. No problem if you solved it with x35 smaller than 3, but I'm going to do it for that to see the correct answer for that one as well. And now you see the answer if I change this 5 that you see here to 3 regarding the path 3 5. In that situation, the maximum flow would be 14, and x35 is 3.